This is the outline for chapter 27 about the circuits. So we will talk about the single loop circuit, the multi-loop circuit, and the ammeter, voltmeter. Although some of the content in chapter 30, okay, we already have talked about the ammeter. Okay, so but here we would like to talk about it again, and then we will also talk about the RC circuit. Okay, so for the single circuit, especially with only resistor, it is really simple. It's really simple. So this is, so there are many texts, but just forget it. It is nothing but E equals IR. We just need to apply the Ohm's law, then that's it, and that's it. Okay, so in the textbook, especially this is a physics textbook, it will try to consider the question in a physics way, okay, which means it uses the power, okay. Actually, in the circuit theory, we seldom, we actually, honestly, I forgot, I have never seen this approach before. Before I really teach this course. So but later on in chapter 31, using the power method is actually have some interesting stuff. Okay, so I still keep it in the slides. 就是说我实际我在教这门课之前，我是没有看过用这种 power 的角度去解电路的，从来没有啊。通常都是用 V 跟 I 就结束，他从来不会去看这个 power 的。但是31章的时候，它会有用 power 的话，会有一个比较有趣的方式，它用一个能量守恒的方式去解电路。我实际上我之前是没有看过，但是我觉得蛮有趣，所以我有保留下来。Okay, so here we talk about one thing called the ideal EMF. Ideal EMF device. Okay, so it is nothing but an ideal battery. Ideal EMF device. Okay, so it is one that lacks any internal resistance. Okay, 它没有所谓的内电阻，它没有内电阻。Okay, the potential difference between its terminal is equal to the EMF. Okay, 你觉得不是很理所当然吗？但是其实现实当中它是不存在，它只是为了方便而已。就是说这个是一个理想的电流源的话，就是说我假设它是3伏就是3伏，1.5伏就1.5伏。但是实际上的话，如果它有内电阻的话，它就不是那样。Okay, so actually in the real world it should be a real EMF device, which means it has some internal resistance. And even though in the practical world, if you have a battery, then it is even worse than this real EMF device. It's even worse than this. Okay, so but actually, to some extent, this kind of model is already good enough, in some sense. Okay, so the potential difference between its terminal is equal to the EMF only if there is no current. Okay, which means if there is current, the EMF between the terminals will be smaller than that voltage. Okay, so this is the perfect one. Okay, so in that case, suppose this is E. Okay, let's say 3 volt or 5 volt. Let's say 5 volt. Okay, no matter how large this I is, okay, it is still 5 volt. So this is an ideal battery. But if it is non-ideal, it will be something like that. There is some small internal resistance. Okay, so if this I is larger, you can expect the potential difference between this internal resistance will be larger. Okay, because it is V equals IR. If I is larger, then the voltage drop across that is larger. So the voltage difference between the node A and node B, between the node A and node B will be this E subtracted by this I times small r. Okay, so if I is larger, this VBA will be smaller. Okay, so that is the real EMF device. 那实际上的话，其实电池的话就更不那个，就是比如说你手机的那个电池，如果它是新出厂的话，它可能其实这个已经 OK， 但是它其实是那样的，就是你新出厂的时候，那个电池有一个内电阻，所以你充满的时候可能会好一些它的电压还是会高一些。你充满的时候其实它已经比这个差一些，因为它的那个 E 还是假设是固定的，就是这里的这个 real EMF device， 它还是假设这个 E 是固定的只是跟那个 I 有关。那真实你的手，比如说真实的一个电池，它其实你充的满一些的话，它的电压会高一些。它用的消耗的比较多之后，它的 V 会降，而且它也会跟你的那个电流有关。你如果很大的电流去，比如说你用一些，比如说你上网上的很厉害去看视频或者是干嘛可以用很大的电流。比如说你在打游戏打游戏的时候用很大的电流，或者是你下载一个 AI 模型在你的手机里面跑那就可以煎蛋，那样的话就会很大的电流，那它的电压也会下降的很厉害。但是除了这种 real EMF device 之外，它就是如果放电放得很厉害的话，它的电压也会下降。所以比如说你用，比如说一些 1.5 伏的那种电池去，比如说放进一些玩具，就比如小朋友会玩一些玩具，它其实是你一直在用，它的电压一直在降到某种程度，它就不工作。但是它不工作的时候，不代表说那个电全部耗光，也许是它放电了一定程度之后，它的 V， 它的电压差不足以让它的那个玩具的那个电路运作起来，所以那个玩具就不运作。但是也许你拿到一个耗电更小的一个电子产品的话，也许它还能运作，有时候是这种状况。Okay, so here we use the energy method for this circuit. Okay, so it is why 用什么？用杀鸡用牛刀so it is like a dW E dq equals EI dt, and then finally EI dt equals I square out, and then finally E equals I out. So you can just forget it. At this case, it is E equals I out. Nothing but the Ohm's law. Okay, so for this single loop circuit, E equals I out is enough. Okay. So here we will always use the potential method. Potential method means usually I will call it voltage. In circuit theory, we always call it voltage rather than potential difference. Okay, so we will also usually call it the voltage rather than potential difference. Actually in circuit theory we will call it KVL, Kirchhoff current law. In chapter 26 we have mentioned something called Kirchhoff current law, which means that if we have a junction, okay, so all the current flowing in equals the sum of all the current flowing out. This is called the Kirchhoff current law. 就是 柯西和夫电流定律啊，电流定律，那自然就也会有这个电压定律，也就是 Kirchhoff voltage law。OK， 这里我们就用一个叫做 Kirchhoff voltage law 的东西，就是刚才我们提那个 RL 电路的时候，其实就是用到这个 Kirchhoff current law 啊，也就是说，我们跑一圈回来的话，它的电压是零，就是用了第24章 In Chapter 24。We have a integration of E dot ds to be 0 if we don't have any magnetic flux changing. Okay, if we don't involve any B field, then we get this. Okay, so yeah, so this is like equals to negative V. Okay, for a whole loop. Okay, to be 0. So this is we will call it the KVL, Kirchhoff current law. In the textbook, it just call it the potential method. Okay, so here is like, okay, so for this circuit, okay, starting from this point, I assume it is a ground. It is a ground. So starting from node 8 and then go across this. Okay, so we go up by E. We go up by E. So actually, in this textbook, it just call it a VA. Okay, maybe you just call it as 0. Okay, so we just replace it as 0. It is still fine because VA and VA cancels. So why not just assume it to be a 0? Makes it even easier. Okay, so if you go from this point to this point, okay, your potential go up by E. Okay, so we have a positive E to be here. And then starting from this node going to here, okay, the potential difference doesn't change at all. We assume all the resistance are lumped here. Okay, so here we have a resistor, and then going through here. Okay, as I mentioned, the current direction is from top to bottom. Okay, so which means it should be like this. VR should be this low is high, this low is low. Okay, so going from this node back to this VA, okay, so going back to 0, and or VA, and then okay, so here we will suffer from a potential drop, higher potential here, lower potential there. So which means we need to subtract by I times R. I times R will be the potential difference across this resistor, but we should remember that, okay, according to the direction of the current, okay, this node should have a higher potential, this one should have a lower potential. So which means, okay, going through the loop like this, okay, we will have potential drop. Okay, so here we need to have a negative IR. Okay, so in this case, E equals IR, or I equals E over R. Okay, so this is nothing but the Ohm's law. This is nothing but the Ohm's law. But still, this is a single loop circuit. Okay, so E equals IR is enough. We don't need to follow this, but maybe for even more complicated circuit, then definitely you need to do so. So it's just like, just let you familiar with it. Just let you familiar with it. Okay, so here in the textbook, it just summarized 3 highlights. One is called the loop rule. For the loop rule, okay, for me, I usually, or even I always call it KVL. I always call it KVL. So it says the algebraic sum, 代数和 of the changes in potential, 就是所有的电压的总和走一圈 encounter in a complete traversal of any loop of a circuit must be 0. 就是你从一个节点走一圈，正负号要算对，它走满一圈的话一定等于0。And then the resistance rule is nothing but the Ohm's law, okay? Ohm's law. And then the EMF rule, okay, I seldom regard it as a rule, although it is like, okay, going from the negative node to the positive node, okay, your potential go up by E, okay? But if you are not familiar with the circuit theory, sometimes you will feel confused, when should I make it positive, when should I make it negative? If you are not familiar with it, Okay, so then you need to follow this step. Okay, from A to B. Okay, whether it's go up or go down. Okay,也许你看着这个例题你会觉得很简单，但是如果是一个比较复杂的问题，就比如说它一个电路啊，我不画元件，它可能长这样的。过去的经验是很多同学会错，就是有时候比如说这个电路里面，我就可能这里有一个电压源，这里有另外一个电压源，然后上上下下的，然后很容易就会搞错啊，很容易就会搞错。比如说这里有个电阻，这里有个电阻，甚至这里也有一个电阻，这里弄几个的话。你如果不熟悉的话，其实还蛮容易搞错这些正号负号的啊，这个是最容易出错的地方。所以如果你觉得困难的话，那你就回归到这种方式哦，你从一个节点去看哦，这个是往上往下，往上往下，怎么定义呢？那些电流电压的方向，当然后面会讲到一些方式去让你的。假设比较简单，因为可能我接近20年前当 TA 这样当那个 circuit analysis TA 的时候改考卷就是会看到有一些同学的话，就是会看到一个电路，每一个节点都定义一个电压，每一个元件都定义一个电流。然后一个很简单的电路定义了10几20个变数出来，然后自己都搞不清楚它在干什么，所以有时候不是定义很多那种变数就很好你定义20几个变数，那就代表说你要写20几个方程你才能解出来嘛，那但是这不 make sense 这不 make sense 因为正常出来的话。顶多就是定义2到3个变数，肯定能够解出来的，不可能定义10几20个变数的。Okay, so this is pretty much how it is. Okay, so for the internal resistance, just as this is a real battery. Okay, here, so this is make the circuit a little bit more difficult. Yeah, but still fine. Okay, so this is a real battery. So inside this real battery, we can consider this is an ideal one with an internal resistance. We denote it as small r. Okay, so the circuit is still capital R. So in that case, the current will be like that. E equals IR. Okay, but this times R plus R. Okay, so why? You can consider this R, this capital R and this small r are in series. So the series resistance will be nothing but R plus capital R. So it will be like that. But if you are not familiar with it, you can actually start from this point. Okay, this is VA, and then we go up by E. Okay, VA and then go up by E, or maybe we can just assume this is a ground node. We start from 0 and then plus E. Okay, this is going up. Okay, we add E here, and then IR. This is a voltage drop, so minus I small r. And then going to here, nothing changed. And then I times capital R and other voltage drop, so minus and other IR. And then go back to the original ground node to be 0. Okay, so this is pretty much it. And then finally, we move these two to the right side and then divide R plus capital R on both sides. So we get I equals E over capital R plus R. So if you would like to draw it out, you would try to cut this circuit and then expand it. It will something look like that. Okay, going from the left to right. Okay, this is a node A, and then the potential going up, and then staying there. Okay, this is the battery. Drop down by the internal resistance, and then stay the same. and then drop down by this capital R, okay, going back to VA or 0 if you like. Okay, so this right hand side will be like going through the loop, and then this is the potential. Okay, so this line tells you the potential over the whole loop. Okay, so